This is Unit 4, Block 1. In Unit 4, we're going to learn about the integral. We're going to talk first here about the definite integral. So first, notice here in writing, the accumulated change of the function f of x. If we want to find the accumulated change of f of x on a given interval, suppose we give you a rate function, f prime of x, that's a continuous function on x equals a to x equals b. So I'm giving you the rate function, the derivative function. Then the accumulated change of the function f of x, so the original function f of x on x equals a to b, is the area between the x-axis and the derivative function, where the area below the x-axis is counted negative. So that's a mouthful. We're going to be working on this for a couple days, trying to sort out exactly what that all means, how the derivative and the area relate back to the function f of x. So let's look at an example here. Suppose a population increases at a fixed rate each year. So again, I am giving you here in this problem a rate function. So notice here I've drawn a graph, r of t equals 400. This function inputs t in years. So here's 1 year, 2 years, 3 years, 4 years, 5 years, 6 years. And it outputs the rate of population increase. So here's 0, 400. At year 0, the population is increasing at a rate of 400 people per year. At year 1, it's still increasing at a rate of 400 people per year. At year 2, still increasing at a rate of 400 people per year. So notice again, I'm not telling you the population, I'm telling you the population rate of change. Notice it is fixed and unchanging. It's a horizontal line. It's always 400 people per year, 400 people per year. I've also given an input-output table with some of the points on the rate function. At 1 year, 400 people per year. At 2 years, 400 people per year, and so forth. So the question is, given this rate function information, I want to know how much did the population increase overall during the first 5 years? Again, what I'm asking for here is accumulated change in the population function. Total accumulated change during the first 5 years. So from year 0 up to year 5, how much did the population go up or how much did the population go down? First, let's just kind of think about this logically. If I told you that a population was increasing by 400 people per 1 year for a total of 5 years, you would take 400 people per year times 5 years, and you would multiply. Notice the years in the numerator cancel with the years in the denominator, and you get 2,000 total people. What that number is telling me is that during the first 5 years, the population increased a total of 2,000 people. Another way to think about it on the graph here, you go from year 0 over to year 1. During that time, you've added 400 people to the population. On the graph here, notice you could think about that visually by saying along the horizontal is 1 year that's passed, and along the vertical is 400 people per year. If you find the area of this rectangle, base 1 year, base times height is the area of that rectangle. The base is 1 year. The height of the rectangle is 400 people per 1 year. And again, it comes out to the same calculation as we had over here. The years in the numerator and denominator cancel, and we get 400 total people. That's the amount of increase that's occurred in that 1 year. And then you could do it again. From year 1 to year 2, another 1 year has passed, and another 400 people per year. And then another from year 2 to year 3, and year 3 to year 4, and year 4 to year 5. Every time another year passes, we're finding another 400 people per year for 1 year. So we add another 400 people to the population. Visually on the graph, we found the area of these rectangles. Notice it's the area between the rate function and the x-axis. And when we find that area between the rate function and the x-axis, we are getting a total accumulated change in the population. In this case, in 5 years, we see that the population increased 2,000 people. One last way to think about this visually. Instead of doing it 1 year at a time, I really could just jump from year 0 all the way up to year 5. So the base times the height, but the base of my rectangle is 5 years, and the height of the function along that entire 5-year span, the height of the function is 400 people per year. So the area of this big rectangle, the area between the rate function and the x-axis is 2,000 people. It's positive. It's saying that the population increased by 2,000 people total during that time span. Okay, so we are finding this in a few different ways to think about it. But given a rate function, we are using the area between the rate function and the x-axis to think about total accumulated change in the population function. So down here in example 1 and example 1a and 1b, we've been given two different examples of what that original population function maybe looked like. So for example, P of t equals 400t plus 5,000 is the population function. It has a y-intercept of 5,000, saying at year 0, the population is 5,000 people. And then it goes over 1 year, up 400 people. Every year, it increases 400 people. Over a year, up 400. Over a year, up 400. Over and over and over. By the time it gets over here to year 5, it will have increased 400 people per year for 5 years in a row, so it will be at a height of 7,000. At year 5, there'll be 7,000 people. Notice, if P of t equals 400t, then its rate, P prime of t, is the derivative of this. Derivative of 400t is just 400. Derivative of 5,000 is 0, so its derivative is 400. That would be 400 people per year. In other words, its derivative is this original function we were talking about a minute ago. Our P of t function from year 0 to year 5, the P of t function increases exactly 2,000 people. Started at 5,000 people. After 5 years passed, it's now at 7,000 people, so it increased 2,000 people. When we were given the rate function, the derivative of P of t up here, P prime of t equals 400, the rate function equals 400, we found the area between the rate function and the x-axis was 2,000 people increase. So again, the area between the rate function and the x-axis is telling us how much the original population function increased overall on that time span. All right, another example related to the same problem, example 1b. This time we have a population function, P of t. This time the P of t function is 400t plus 300. So this is a population function that at year 0 has 300 people, but it is still linear. It's increasing at a rate of 400 people per year. Over 1, up 400. over 1 up 400, over 1 up 400, over and over and over. By the time it gets to year 5, it will have increased a total of 2,000 people. So there'll be 2,300 people total. Every year, we add 400 people to the population. There's the population function P of t, but again, notice its derivative, P prime, is 400, our original red rate function. So this function looks a little different than the example 1a function that we dealt with a moment ago, but really the only difference between them is the vertical shift. In example 1a, we had a y-intercept of 5,000. In example 1b, we have a y-intercept of 300. But both example 1a and example 1b have a rate, p prime of t equals 400. They have the same derivative. And if you look, example 1b starts at year 0 at a population of 300. And after 5 years pass, the population increases 2,000 people, just like what happened in example 1a. And we only needed the rate function to help us figure that out. The rate function, which was r of t equals 400, finding the area between the rate function and the x-axis was 400, positive 400, this area, which told us how much the population increased in total during that time period. So let's read this one more time. Suppose f prime is a continuous function from x equals a to x equals b. Again, you're given f prime, given the rate function, f prime. Then we can use that rate function to find accumulated change. The accumulated change of f of x, the original f of x function on that interval, is the area between the x-axis and the derivative function, where we are going to count area below the x-axis as negative, and we're going to see that in the next example.